Okay, we'll take the next question. Again, a question from Wave Optics. In a YDSC with two identical slates, when upper slate is covered with thin, perfectly transparent sheet of mica, intensity at the center of the screen reduces to 75% of the initial value. Okay. Second minima is observed to be above this point and third maxima below it. Which of the following cannot be a possible value of phase difference caused by the mica sheet? Okay, so these are the four options given. Okay. See, first thing you have to understand here, the mica sheet is introduced, okay, in front of the upper slate, the intensity reduces to 75% of the initial value. That means the intensity, if we call it as I dash, this will become 75% is 3 by 4 of initial value. Initial value intensity at the central maxima, we know that it is 4i. So this is now 3i. Okay. And if you just put the resultant intensity formula, the resultant intensity formula is I1, which is I, plus I2, which is again I, plus 2 root of I1, I2 cos phi. And now this is equal to 3I. Okay. The resultant intensity formula is I1 plus I2 plus 2 root I1, I2 into cos phi. So if you just simplify this, this will be, this is 2I common. If you just take 2I plus 2I cos phi. So this implies 3I minus 2I is I divided by 2I is equal to cos phi. Okay. So cos phi is half. That means phi will be 60 degrees. That is pi by 3. Okay. Now if you just look at the options, okay, what is given? Second minima is observed to be above this point and third minima is below this. Second minima is above. So what is this value actually? 60 degrees. 60 degrees, does it lie? See, for second minima, okay, for second minima, what should be the phase difference? Phase difference should be equal to 3 pi. Correct. And second maxima, third maxima. For third maxima, what is the phase difference? 2 pi, 2 pi, 2 pi. So that is 6 pi. Okay. So if you just check these values, 3 pi and 6 pi. This is 3 into 180. And this is 6 into 180. 3 into 180 is nothing but 540. And 6 into 180 is 18 6 108, 1080. So if you just look at this, this is 60 degrees. Okay, this does not lie in between these two. Correct. So therefore, if you just look at this, pi by 3, 13 pi by 3, 11 pi by 3. So this value, this should lie between 3 pi and 6 pi. Okay, but it is not lying. Okay, so therefore, which of the following cannot be a possible value of the phase difference? It is this, pi by 3. It does not lie between these two. Okay, we'll see another question. Two resistances R and 2R connected in parallel across a battery. If total current drawn is 3 ampere, current through resistor R is, okay, so this is a parallel connection. Okay, so total current is given. Total current, if you call it as I, if I is 3 ampere, let's call this as 2R and this as R. So here if current is I1 and here it is I2. Okay, so we know that I1 is to I2. The current is always inversely proportional to the resistances. So 1 upon 2R is to 1 upon R. If we just calculate the ratio, I1 is to I2 will be equal to 1 is to 2. Okay. So lower resistance, more current, high resistance, less current. We want I1, right? Current through, no, resistance R, we want I2. So from this, I2 will be equal to this 2 divided by 2 plus 1, that is 3, multiplied by the total current, that is 3. So 2 amperes. So less resistance. So I2, here the current will be 2 amperes and here it will be 1 ampere. So answer is 2 ampere, option second. Okay, another question on projectile motion. A projectile is fired at an angle theta and speed u. Ratio of kinetic energy at the highest point to that at the point of projection. Okay, 4 options are given. See, in projectile motion, okay, this is the velocity of projection u. This is theta. At the highest point, there is only the horizontal component of velocity which remains. That is u cos theta. The vertical component is 0 at the highest point. Okay, so at the highest point, if we say kinetic energy as K2, K2 is equal to half m u square cos square theta. And at the point of projection, if we call it as K1, here it is just half m u square. Okay, so if we do K2 by K1, what will remain? This will get cancelled and answer is cos square theta. That's it. First option. Hello. Hello all. We'll take the next question. What should be the value of refractive index mu of the glass rod placed in air so that light entering through the flat surface of the rod does not cross the curved surface of the rod? Okay. See, this is a very standard question. This ray of light is not allowed to come out of the curved surface of the rod. Okay. So we'll try to solve it. See, we can apply Snell's law at this surface first. If you apply Snell's law, what we can write is mu is equal to sine I upon sine R. So from this, sine R will be equal to sine I upon mu. You can call this as equation 1. Now, the ray should not come out, right? So that means here there should be total internal reflection at this surface. The ray has entered here. So here, if the ray has to suffer total internal reflection, that means this angle R dash should be greater than the critical angle, right? So you can call this point at P for total internal reflection at point P. R dash should be greater than the critical angle C. Correct? We'll call critical angle C. That means I can also write that sine of R dash should be greater than sine of C. We know that sine of C is nothing but it is equal to the reciprocal of the refractive index of this glass medium. So therefore, I can write sine R dash is greater than 1 upon mu. Correct? Now, if you look at this triangle here, if you look at this triangle, R dash plus R plus 90, this total is 180, right? So that means, what is R dash? R dash, can we write it as 90 minus R? So if you just put it here, this will be sine 90 minus R is equal to 1 over mu. Sine of 90 minus R is nothing but cos R. Cos R is 1 upon mu. Now, if you just refer the first trigonometric identity, sin square theta plus cos square theta is equal to 1. So cos of R can be written as root of, this implies root of 1 minus sin square R is equal to 1 upon mu. Correct? Now see, from equation 1, sin R can be written as sin I upon mu. Correct? So from equation 1, if you just substitute for sin R, we have 1 minus sin square I upon mu square under root is equal to 1 upon mu. So if you just simplify this, if you remove this square root, then here we'll have 1 upon mu square. So mu square minus sine square, if you just simplify it, what you get? Mu square minus sine square minus sine square I, mu square minus sine square I is greater than 1. Correct? So mu should be greater than 1 plus, just simplify this, I'll write it here. There is no space. Okay. So mu should be greater than root of 1 plus sine square I. This. If you just simplify this. Now mu is greater than root of 1 plus sine square I. Now what is the maximum value of angle of incidence? Angle of incidence can take the maximum value as 90 degrees. So that means mu is greater than root of 1 plus sine square 90, which is equal to 1. So therefore mu is greater than root 2. This should be the answer. So the refractive index of the glass rod, so that the ray does not come out of the curved surface, that means it undergoes total internal reflection at P. For the condition to be satisfied, the refractive index of the glass should be greater than root 2. Okay, we'll take this question. Again, a question on ray optics. Ray of light passes from air into a glass slab. Angle of incidence increased from 0 to 80 degrees. Which of the following statements about angle of refraction is most accurate? Okay, A, angle of refraction first increases, then decreases, always remains less than this. Angle of refraction decreases continuously as incidence angle increases. Angle of refraction always equals wrong. Angle of refraction always remains constant. This is also wrong. So C and D are already ruled out. See, what will happen? The angle of refraction, it will first increase, right? Angle of refraction, first it increases as angle of incidence increases. After that, what happens? It will reach a limiting value. One thing is, it is always less than angle of incidence. This also we should note. It is always less than angle of incidence. Then what happens? On further increase, then the angle of refraction, it will reach a limiting value. After that, it will not increase. It will reach a limiting value. Now, see, this behavior of the angle of refraction is because of Snell's law. That is, n1 sine I is equal to n2 sine R, provided n2 is greater than n1. That means the second medium is a denser medium, first medium is a rarer medium. So if you just look at this option, the continuous, angle of refraction first increases, then decreases, and always less than this. So option A is the correct option.